Now let's have a look at the questions in the handout. Question 1. We're given a straight pile installed into a layer soil with 15 meters of stiff clay overlying a sand layer. And we're given the soil properties and 3 assumptions of the pile length. Under the assumptions A and B, we have the pile length to be 12 meters and 14 meters. So the pile will be embedded in the clay layer. So we can directly use this equation QU equals slip friction, which is C, the circumstance of the pile, times the length embedded in the clay, times QS, which is the unit shaft resistance of the pile in the clay, plus the pile toe area times the undrained shear strength of clay times and bearing factor NT. And the QS is calculated using the undrained shear strength times relation factor. And NT factor equals a recommended value of 9 for pile diameter smaller than 0.5 meters, or 7 for pile diameter between 0.5 meters and 1 meter, or 6 for pile diameter greater than 1 meters. Notably, we did not consider the impact of the sand layer on this calculation of QU because the clay layer is usually considered as a weaker layer than a sand layer. So the slip surface is unlikely extending into the stronger underlying layer, so we do not need to consider the impact of the underlying sand layer on the bearing capacity of the pile. Then assumption C for the pile length is 16 meters. Then we have a pile toe inserted into the sand layer by 1 meter. Like this. We have 15 meters of clay and a pile, embedded length of 16 meters. So clay and sand. When this pile is vertically loaded, we're going to have a slip surface F failure like this. Since the clay layer is considered as weaker than a sand layer, so the slip surface may extend into the clay layer and therefore reduce the bearing capacity calculated using the strength parameters of the sand. Under this kind of scenario, we're going to use a principle of interpolation. So we're going to have 2 imaginary piles. The first one is equal to 15 meters. And the pile toe is at the interface of these 2 layers. And the other imaginary pile, which is 15 meters plus 6 times of pile diameter This 6 times of pile diameter is going to allow for the development of the slip surface, so that we can say pile toe bearing capacity is not affected by the overlying sand layer. Then we need to determine the end bearing capacity QT for these two imaginary piles. So for the 15-meter imaginary pile, we denoted QT1, and it's equal to AT times NT times SU of the clay layer, and this NT depends on the pile diameter, and QT2 for the second imaginary pile, it is equal to AT times NC times sigma V prime at 15 meters plus 6 dp. And the NC for this sand layer depends on the friction angle here, given as 32 degrees. So from CFEM we can obtain a range for NC of 50 to 120, and to be conservative we select NC of 50, and then we will use a linear interpolation to find the end bearing capacity of the 16-meter pile. So imaginary pile 1, I1, sitting on the interface, and the real pile, and then the imaginary pile 2, say I2, and QT1, the real QT, and the QT2, and the thickness of this total range is 6 dp. So linear interpolation tells us QT is equal to the total difference of these two QTs, QT2 minus QT1, divided by the total thickness, which is 6 dp, times the depth of the real pile inserted into the sand layer, which is 1 meter, plus QT1, and then the total ultimate bearing capacity QU can be written as QS plus QT, where QS is equal to alpha SU times C, the circumference, times the length embedded in the clay layer, which is 15 meters, plus KS times tangent delta times the average vertical effective stress between 15 meters of depth and 16 meters of depth, times C times the pile length inserted into the sand layer.